Good evening, everyone. I'm Anish Andekar, PhD candidate from Aerospace Engineering, IISc Bangalore. Welcome to today's live session for the NPTEL course, Computational Mathematics with SageMath. As is the custom every week, we'll be going through a few practice problems which will further elucidate the concepts taught in this particular week's lectures. So the first problem, the first example that we have for today is involves verifying vector, a few properties of vectors. The first is the triangular inequality, wherein we check if the mod of sum of two vectors is less or equal to sum of the modulus of the two vectors independently. To do so, we'll first start by writing down a vector u, which is in field rational field QQ and which has 4 dimensions. We'll similarly write down a vector v with same number of same dimensions. For the first property, the left hand side is simply defined as norm of u plus v, where norm would refer to the L2 norm of u and v, whereas the right hand side refers to sum of the norms of u and v individually. With this in mind, I'll just print those values and then we'll check if this property is indeed verified for this randomly chosen u and v. So you can see that the norm of the sum is less, in this case turns out to be less than sum of the individual norms. The second property is in, basically involves norm of square of the norm of the sum and square of the norm of the difference between those two vectors, and whether it is equal to twice of the sum of square of the individual norms. So that is how we define LHS02 and RHS02. Uh, thus, LHS number 2 and RHS number 2 based on summing the respective norms. And if I print out their values, we see that both the LHS and RHS satisfy the same value, have the same value, and this basically satisfies this second identity that we have. So with the chosen vectors, with the randomly chosen vectors, we can see that these properties are indeed verified for the vectors. Okay, I believe this is fairly straightforward. If you have any questions here, you can ask them now. Okay, we move on to the second example. Here we have been asked to consider an inner product P3 of x, which is defined by inner product P comma Q is P of 0 into Q of 0 plus P of 1 into Q of 1 plus P of 2 into Q of 2 plus P of 3 into Q of 3. So at x equal to 0 and 2, 3, we calculate the polynomial, we evaluate the polynomials P and Q, multiply them and sum up the answer to calculate the inner product. And using this definition of inner product P3 of x, we have been asked to find the angle between two polynomials which are given as 2 minus x square and 1 plus x square plus x cube. The second part of the example asks us to find the orthogonal projection of 1 plus x square plus x cube onto 2 minus x square with respect to this inner product that has been defined. So we first begin by writing down the definition of the inner product between polynomials f and g, and we just write it as the sum of f of f at evaluated at x equal to y into g evaluated at x equal to y for I in the range of 4. So I will basically verify as 0, 1, 2 and 3, and f and g will be evaluated at all these 4 points multiplied, and that should give us an array with 4 terms P0, Q0, P1, Q1, P2, Q2 and P3, Q3. The sum of that array is basically I've written it as the variable a, and then I'm returning that variable as my answer for the inner product between polynomials f and g. Next step, we define the variable x So to define the symbolic expressions f and g, we first define it's a good habit to initialize the variable, which is x in this case. Then we define both the polynomials f of x and g of x as 1 plus x square plus x cube and 2 minus x square respectively. If I print those out, it basically gives me the function map when I use the show command. To find the angle theta between uh, these two polynomials p and q, will be using this definition here, where cos of theta is defined as inner product between the two chosen vectors divided by norm of product of the norm of those individual vectors. So in our case, how that goes is basically inner product of f and g is evaluated as inner product polynomial of f comma g. To calculate norm of f and norm of g, we basically take the square root of the inner product of f with respect to itself and g with respect to itself respectively. That should give us the inner products of f and g, the norms of f and g respectively. The angle is simply cos of that angle is simply inner product of fg divided by norm of f into norm of g. We are doing arc cos to do basically in to basically find the angle theta from this, and then this value, the output of the arc cos function will come in terms of radians, and we are just scaling it with 180 by 5 180 by pi to get us the angle in terms of degrees. So if I run this command and print all the necessary like steps in between, what do I see? I get inner product as minus 304 and norms as 42.9 and 7.6 respectively, which gives me the angle between F and G to be 158.44 degrees. To calculate projection of V on U, we'll be using this definition, wherein projection of orthogonal projection of V on U is basically inner product of V comma U upon inner product of U comma U into vector U itself. So I've just bundled this all formulation into this function proj, which takes arguments as v, u, and some inner product function. So the projection basically becomes is written as like the same definition: inner product of vu upon inner product of uu whole multiplied with the vector u, and we return the projection. In our case, since we are interested in calculating projection of f on g, we basically pass the arguments in the correct order. So f first, then g, and the function inner product polynomial, and this whole thing becomes a different functions of x itself. So that is how we are expressing it. And once we do this, I'll just evaluate the projection of f on g. Then, just to confirm if this is indeed the orthogonal projection of f on g, I am subtracting that projection from f and taking the inner product of the residue with respect to g. I expect, since this is the orthogonal projection, I expect the inner product of the residue with respect to g to vanish. If I run this cell, I see that the projection looks like 152 by 29 x square minus 304 by 29, and the dot product of the residue of f of x after removing the orthogonal projection is, as expected, 0. So this completes this example. If there are any doubts here, you can ask them now. Since there are no doubts here, this seems to be quite clear. The third example that we have is, we have been asked to choose a random 4x4 real symmetric positive definite matrix A and define an inner product on R4, which is defined as inner product of x comma y is basically y transpose ax, or the dot product between y and ax. and we have been asked to verify the cosine law under this inner product. So how do we go about defining this random matrix, right? So which also needs to be, by the way, positive definite. So a simple way would be to simply define, say, like a diagonal matrix itself, and if you ensure that all the entries are positive, it basically becomes a positive definite matrix. So that is how I start. I define a matrix B first by taking 4 positive diagonal entries, and then I add some off diagonal terms while and then I add some off diagonal terms to create an upper triangular matrix. I add the transpose of that matrix to itself to create a symmetric matrix, and I'm basically adjusting the diagonal term, increasing or decreasing it till the eigenvalue of the A matrix, which is B plus B transpose, turns out to be, all of them turn out to be positive, making it a positive definite matrix. So by trial and error, I've arrived at a configuration which I've shown here, and if I use this type of upper triangular matrix, my A matrix looks like this. Just to check if A is both symmetric and positive definite, I'll be using A dot is symmetric and A dot is positive definite uh, methods on the matrix A. If I print out the output, I see that A is both symmetric as well as positive definite. Next, I define the inner product in the way that has been defined to us. Inner product A of u comma v is basically v dot product, it's basically the dot product of vector v with A into u. Now we choose two random vectors u and v. So they belong to the rational field. Again, have uh, four dimension 4. So I run this. Now I'm interested in seeing what what the cos of the angle between u and v looks like. So that, as you have seen in the definition shown in earlier example, it's basically the inner product of uv divided by norm of u and into norm of v. So I'm basically taking the square root of inner product of u comma u with inner product multiplied with inner product of v comma v, and the cos evaluates to be minus 0.72. Next, we want to see the cosine law. So the cosine law in a nutshell looks like this, where suppose you have two vectors A and B, then the third side connecting those two vectors C, which can be defined as A minus B, and the norm of C basically follows this equation where norm of C square is norm of A square plus norm of B square minus twice of inner product of A comma B. Uh, if this is an inner product space, we should be able to satisfy this relation. So that is why we have been asked to check this. So we first begin by specifying a vector u which equals the difference, specifying the vector w which equals the difference between vectors u and v. If I print all three vectors once, I see them looking like this: u, v, and w is equal to u minus v. Next, I calculate the norms of w, u, and v. All of them, again, like based on the earlier definitions, it's simply the inner product of the vector with respect to itself, and then taking a square root. So that is how we are specifying norm w, norm u, and norm v as the norms of vectors v, u, and w, u, and v respectively. So these are how the norms end up looking like: norm w, norm u, and norm of v. The cosine law, as we specified earlier, we basically take square of norm of w on the left hand side, and the right hand side is square of norm of u, the square of norm of v, minus twice of inner product of u comma v. We'll print both LHS and RHS, and then we'll be checking if they are indeed equal. So the LHS and RHS in our case both evaluate to 720, and thus this relation. Thus, the cosine law holds true. It has been verified for a random input under this defined inner product with this particular chosen matrix. Okay, so any doubts in this example? Okay, if this is clear, we'll move to the next example. The fourth example asks us to define an inner product space on C with the domain going from 0 to 2 pi as follows. Inner product between two functions f and g is basically the integral from 0 to 2 pi f of x g of x dx, and then we are asked to show whether cos of nx and cos of mx are indeed orthogonal to each other as defined by this inner product for any two integers m and n. Okay. As is a good practice, we first specify the variable which is x, and here we have randomly chosen n equal to 1 and m equal to 2. We define f of x and g of x to be sine of. Okay, I think I'm showing all three. Huh? Okay, we have written on f of x and g of x first as sine of nx and sine of mx. If I show them, this is how the map looks like: x going to sine x and x going to sine of 2x. The inner product between f and g is basically integral of f of x into g of x for x varying from 0 to 2 pi, which is this, which is the definition that we have been provided with. And if I now do say inner product of sine of nx and sine of nx and sine of mx, I basically get the inner product of sine of x and sine of 2x is basically 0, which means that they are orthogonal to each other. If I do the same thing for cos of nx and cos of mx, now f of x and g of x are defined to be cos x and cos 2x, which is what the maps should show, and that is indeed correct. Then if we I now calculate the inner product again, so the inner product between cos of x and cos of 2x is indeed 0. Finally, I'm just playing around with cos of nx and sine of mx, and if I run the inner product, this also turns out to be 0. So basically, for this inner product, for the inner product uh, on the C0 to 2 pi, we have been able to show the relation that we have been asked for. Okay, any doubts here? Or if it is clear, then we can go to the next one. Okay, so the next example here, we have been told that let Tm going from R square to R square, so real 2 to real 2 space denote orthogonal projection on the line y is equal to mx. We have been given that it can be shown that Pm of V is basically 1 over 1 plus m square into a 2 by 2 matrix 1 m square multiplied by the vector v. So that should give us the projection, orthogonal projection Pm of v on the line y is equal to mx. And now we have been told to find the projection of the vector 2 comma 1. So Pm going from r square to r square denotes the orthogonal projection on the line y is equal to mx, and we have been given that the projection Pm for a vector v is basically product of a 2 by 2 matrix with the vector v. Next, we have been given a vector v equal to 2 comma 1, and we have been asked to find its orthogonal projection about the line y is equal to 2x, and then plot the vector line as well as the orthogonal projection. Okay, so we start off first again by specifying the vector v on the rational field QQ, 2 comma 1. Next, we specify the variables x and m, and then the line, which is y of x, written as an expression, is basically m into x. Next, we'll be using this projection function Pm of v, and it's written as projection on, orthogonal projection about the line for a given vector v. It takes two arguments, m and v, denoting slope of the line and the vector v, and it is basically defined as 1 by 1 plus m square into a 2 by 2 matrix on the QQ field, which is 1 m m square. So same as what we have been given. And then the projection is simply this 2 by 2 matrix Pm into the vector v. We have been given a line y is equal to 2x, so the slope m equals 2. The orthogonal projection of vector v about this line is can basically be calculated by the function that we have defined above using m and v. So m is specified as 2, v is specified as 2 comma 1, and if I calculate the projection looks like this. So 4 by 5 comma 8 by 5. If I now plot the different components, so I'll be plotting the vector v in with the label vector. I'll be also plotting projection of vector v in the red color, and finally I'll be plotting the line y is equal to mx. So it will go from origin 0 comma 0 and the point 1 comma m, and it is basically a line with color black. If I plot all these three, what do I see? So this is how I see. So this is my vector in the blue color, 2 comma 1. This is my line y is equal to 2x. It's going from 0 0 to 1 comma 2, and the projection of this vector on this line is basically this much. If I say change this point to say 2 comma minus 1, and if I go through the whole process again, I'll get a projection to be 0. So this basically means that the line and vector are perpendicular to each other. Okay, uh, any doubts with this particular example? Okay, since this is clear, we'll move on to the next one. So the next example, 6, we have been given let QM be a map going from R square to R square, denote the reflection about the line y is equal to mx. Then we are told that Qm of some vector v can be defined as 1 over 1 plus m square, 1 minus m square, 2m, 2m, and m square minus 1 into the vector v. We have been asked to find the reflection of the vector 2 comma 4 about the line y is equal to x by 2. Then we have been also further asked to plot the line vector as well as reflection of the vector with respect to the line. Okay, again, same process. Define the vector v, which is on the rational field QQ, 2 comma 4. Next, we, as is a good practice, specify the variables x comma m, and then define the line y is equal to mx as the function y of x. Now, the reflection about the line of a given vector v, that function is defined using this name reflection line vector. It takes two arguments, m comma v, m denoting the slope, v denoting the vector, and qm is basically the appropriate transformation matrix given as 1 over 1 plus m square. into a matrix on the rational field QQ with the entries 1 minus m square, 2m, 2m, and m square minus 1. So same as that we have been given above. And then we multiply this matrix with our input vector v to get the reflection of the vector. Next, we have the slope given as m. Slope is half. Reflection of the vector v is basically we call this function with the slope half and above defined vector v. So the answer turns out to be 22 by 5 comma minus 4 by 5. Finally, we plot all the relevant output, which is the vector v, reflection of the vector v about the line, and the line itself. So the line is again defined by the two endpoints of the line, origin and some point k comma mk. So here I have basically chosen 4 comma 4m, and if I plot this, this is how my output looks like. So this is my vector v, this is my reflection, and the blue one is my line. Okay, so yeah, any doubts with this particular example? Okay, it seems this is also clear. The next example that we have been given that a matrix A is, we have been given a matrix A, which is a 3 by 3 symmetric matrix given by the entries as shown here. Next, we have been asked to define an inner product space on RQ uh, for two vectors u comma v, which is basically the dot product of v and au. Then, using Gram-Schmidt orthogonalization process, we have been asked to find an orthonormal basis from the standard basis vector e1, e2, e3 with respect to the above inner product. Okay, let us begin. So the matrix A is basically 2 minus 1 0 minus 1 2 0 and 0 1 minus 2. Next, I define vectors e1, e2, e3. We have been told that they are the standard basis vectors. So 1 0 0, 0 1 0, and 0 0 1. As a as is the as a like a custom or a precaution, we check the linear independence of any basis. So I define standard basis as capital E containing small e1, e2, and e3 respectively, and then with respect to the over lying vector space, which is RR3, I define, I check the linear independence of this particular basis set. So the linear dependence turns out to be an empty set, which basically tells us that this is a linearly independent set. Next, I define inner product between u and v as the dot product between v and a into u. I'm also defining projection orthogonal projection of v with respect to vector u using the so like the same formula that we have seen above. We find out the inner product between v and u, divide it with the inner product of u with itself, multiply the scalar whatever we get with the vector u. So this will give us the projection of v on u, and norm of a particular vector, just for the sake of it, I'm defining it as square root between square root of the inner product between u and u itself. So that gives me norm with respect to our space. Next, I define Gram-Schmidt orthogonalization. So it takes a single argument S, which is a set containing three vectors. which is a set containing vectors. So in our case, we only have three vectors. So the first element of this, so the first element is basically the first vector S0 divided by its norm. So that basically makes, if suppose we are given like any other, here we are inputting standard basis, so the norm is actually 1 by default, but in case if it was not 1, we basically divide it with the norm of the vector itself to create the first element, which is normal, uh, which has norm 1. Second element is defined as like the first element, the second element of set S minus the projection of uh, the second element of set S with respect to the normal element L1. So this projection will basically calculate how S1 depends on element, how the component of S1 along element L1, and once we subtract that, we get L2I, which is basically S1 or residue of S1 removing any component along L1. Just to check if this is indeed orthogonal, I am doing this check where I am calculating the inner product between L2I and L1. If this inner product is indeed 0, we calculate the second element in the uh, second orthonormal element L2S, L2I by norm of L2I. Otherwise, we sorry. Otherwise we give an error telling us that we obtained an error in the second element. Third element, same thing. Take the third element from set S, calculate its projection with respect to L1, and remove that part to get residue L3I. Similarly, from L3I, we remove the residue, which is along, uh, we calculate the residue by removing the orthogonal projection of L3I along the second element, which was L2. So by doing so, we now define, again we check the inner products between L3I L1 and L3I L2. Both of them should vanish by doing so. If they do vanish, we calculate the third element as L3I by norm of L3I. If for some reason this we run into some trouble, we just uh, print out an error message along with the inner products respectively. Finally, once this all loop is done, we write, we export, sorry, we return L1, L2, and L3 with three significant digits evaluated in numerical form, numerical values. Sorry. So this defines this Gram-Schmidt orthogonalization process. And now I have already defined my set E to be E1, E2, and E3, and then I run this function to obtain the set E1. If I run this, I get two elements, which sorry, I get three by three elements which look like this. Okay, so first is basically 1 by root 2. Second is some, I just written the normal values. What do I see? Okay, I think it's the way. Right. So this is how my three orthonormal uh, basis looks like. And if I have to verify my answer, how what I would do is basically run the loop, run a loop where I'm taking the I and any I and jth entries and calculating the inner product between E1 of I and E1 of j. So that should tell me how my inner product looks like. If this is indeed an orthonormal basis, for each vector, the inner product of each vector with itself should be 1, and inner product of any two distinct vectors should vanish to 0. We have already incorporated a check, but just to verify. So, like the inner product of the zeroth element is basic with respect to itself is 1. Inner product of the first element and the second element, both with respect to each other, are 1. And whereas any two distinct elements, the inner product simply goes to 0. Okay, so this basically calculates an orthonormal basis from the standard vectors E1, E2, E3 with respect to the inner product that we have been given. Okay, any doubts here, or like all any of the problems that we have done so far? Is this clear so far? If you have any doubts, you may uh, raise or post it in the chat box itself. Okay, it seems this is clear. We'll move on to the next example. So, example number 8, we have been asked to consider an inner product P3 of R defined by inner product between P and QS, P of 0 into Q of 0 plus P of 1 into Q of 1 plus P of 2 into Q of 2 plus P of 3 into Q of 3. So, this is basically the inner product between two polynomials P and Q. Next, we have been asked to use Gram-Schmidt orthogonalization process to find an orthonormal basis emerging from the standard basis, which for this case is basically 1 x square and x cube, and this particular inner product. So, as is a good practice, we first define the variable x. Next, we define four. Sorry. Next, we define four functions: f1 of x, f2 of x, f3 of x, and f4 of x, respectively as 1 x square and x cube. So this creates f1 to f4 together becomes my standard basis. If I print them, the map going from x looks alright. Next, we define the inner product between polynomials f and g using the above definition, which is basically f of 0 into g of 0 plus f of 1 into g of 1 plus f of 2 into g of 2 and f of 3 into g of 3. To find the norm of a particular polynomial f of x with respect to this inner product polynomial, inner product between polynomials, I basically invoke the inner product of f comma f and then take its square root. Next, if I sorry, next I again define the projection of orthogonal projection of polynomial f onto G as inner product between f and G divided by inner product between G and G itself, or this whole factor multiplied by the polynomial G. Right. So I I just to check like how this looks like, I expect my norm of f1 to be equal to 4. So if I run this, sorry, norm of f1 to be equal to 2 square root of 4, and inner product between f and say like f1 and f2, if I take, that should be, sorry, if I take the inner product between F1 and F2, 36. So this can be verified wherein the F2 of 0 is basically 0 and F2 of 1, 2 and 3 are basically 1, 2 and 3 respectively. So just to check if the inner product and norms are working fine, and then the orthogonal projection also. So to calculate an orthonormal basis from the standard basis, I first define few functions g1 to g4, and they are defined as follows: g1 takes the value of f1, g2 takes the value of f2 minus the projection of f2 with respect to g1. So that basically makes g2 to be orthogonal to g1. Similarly, g3 is defined as f3 minus projection of f3 with respect to g1 and minus projection of g3 with respect to g2, and g4 is similarly defined as f4 minus all the projections with respect to g1, g2 and g3 respectively. So this will create four polynomials g1, g2, g3, g4, which should be orthogonal to each other. So if I see how the set looks like, so how it looks like. So let's do a show, right? So you have say x cube minus 9 by 2 x square plus 47 by 10 x minus 3 by 10, 1 square minus 3x plus 2 and x minus 3 by 2. Now I define few polynomials h1, h2, h3 and h4 of the variable x as g1 by norm of g1, g2 by norm of g2, g3 by norm of g3 and g4 by norm of g4. If I also print, if I also show the set h1, h2, h3, h4, this is how it looks like. Okay, so if I now, what I'll now do is basically for x going from 0 to 3, I'll be plotting h1, h2, h3, h4 and providing appropriate labels. This is how it looks like. So h1 is simply 1 by 2, so straight line. It's a it's a constant. H2 is a straight line. Is intersecting at x equal to 1.5. H3 looks like quadratic function and h4 looks like a cubic function. So these are my polynomials, four polynomial bases. To check if they satisfy the necessary conditions, I'll run through the same verification that I have done for the earlier example, I wherein I define a set containing the new orthonormal basis, and then for each of the term belonging to that basis, I take inner product uh, with respect to other terms. So I will print out which term I comma j comma inner product polynomial of set s I comma s j. So 0, 0 is 1, 1, 1 is 1, 2, 2 is 1, and 3, 3 is 1. So the inner product of H1, H2, H3, H4 with respect to itself, all of those are 1, whereas inner product with respect to any distinct Hi comma Hj where I doesn't equal j goes to 0, which basically is the definition of an orthonormal basis. Okay, so for this particular inner product and this set of standard bases, we have been able to uh, use the Gram-Schmidt orthogonalization to find a new orthonormal basis. Okay, any doubts with this? Next example, we have been asked to find the QR factorization of a 3 by 3 matrix A, which is given here, and use that to solve Ax equal to B, where B is a vector size 3 given as follows. So we first define A and B matrix, A as a matrix on QQ and B as again on, sorry, B again as a vector on QQ. I'll just print what they look like. So yeah, so this is as given. Next we want to look at, next we'll be using a symbolic ring variable. So just to see how the help on that looks like. Okay, so it it takes a it takes a name as well as the number of, say, variables going from 0 to n minus 1, and it outputs like a tuple of variables. So we'll be using this to basically to find ax equal to b. We'll basically be using this symbolic variable to define a vector, define a 3 by define a vector of size 3 with the entries as variables x0, x1, and x2. Before going to the QR factorization, I'll be first going through a simpler least square method, or where we try to minimize the error. So the error is defined as matrix A into vector x minus b, and then we define function f to be sum of uh, square of the error terms. So if I do, say, show error, so the error basically is a ax minus b, a 3 by 1 vector, and sum of square of each of the terms of the vectors basically gives me the function f. Next, I define the gradient of this function f by invoking f dot gradient. This again gives me a 3 by 1 vector, and now I solve for this part. Now I solve for the gradient of f going to 0, which means that each of the three terms in the gradient should go to 0. And I solve for the variable x, which actually contains x0, x1, and x2 as defined here. And I'm asking it to find, to give the solution in the form of dictionary and then print it. So the solution ends up looking like this: 45 by 8, 5 by 4, and minus 25 by 8. So which is basically 5.625, 1.25, and minus 3.125. So the optimal point x star is nothing but uh, x1, which is a vector S0 of D for D in X with 4 digits. So basically this vector itself. And then the closest point to B becomes A into X. So 10, 5, and 15. So in this case, this given example Ax equal to B is perfectly solvable, and that we could have also checked either through, say, looking at determinant of A, whether A is singular or not. A is indeed invertible, which we could have used also to find the solution. Using QR factorization, we first change the ring to RDF for both matrix A and vector B. And the QR factorization is nothing but A dot QR, right? And R is simply an upper triangular matrix. Next, if I have to calculate what sorry, Q is an R is an upper triangular matrix and Q is a orthogonal matrix. So Q transpose is basically I. If I now wish to calculate Ax equal to B, I will substitute A is equal to QR. So my equation becomes QR is equal to B. Multiplying both the LHS and RHS with Q transpose, I get Q transpose QR is equal to Q transpose B. So the RHS I am now defining as B1 is Q transpose B, and the LHS Q transpose Q Rx, which translates to Rx because Q is orthogonal. So my Rx equals B1, and or rather R1x 1 equal to B1, and then I use that to solve for x, which is basically R inverse B1. So if I do that, I get my answer to be 5.625, 1.25, and minus 3.125. Okay, so this is the answer that I obtained from QR decomposition, and this is what I obtained from uh, the least square method. So basically, my optimal point is uh, the same one, 5.625, 1.25, and minus 3.125. Okay, so this solves this particular example. Any doubts with this one? Okay, uh, seems this is clear. Next example that we have involves finding least square solution for the system of equations Ax equal to B. So A is given as a 5 by 3 matrix and B is a 5 by 1 vector. So a 5 by 3 matrix multiplied by with a 3 by 1 vector X should, we want to check if it does give B. So let us first start by specifying A and B, which are matrices, which is a matrix in the field QQ, 5 by 3 matrix, and B is a 5 by 1 vector again in QQ. So this gives you A and B respectively. If a solution exists, if an exact solution exists for B, it should lie in the column space of A. Like I think that is quite self-evident that if the column space of A contains B, we could find an exact solution. So to check that, we basically check if B is in the uh, column space of A, and turns out that the answer is false. Next, if next we define a random variable, sorry, a series of random variables on uh, x, starting with the notation x, so x0, x1, x2, with number of variables as m. So m is 3, we have already defined here. That gives me, using that, I'll define the capital vector x. So capital X is nothing but x0, x1, x2. Next, we calculate error function and the gradient. So error is defined as ax minus a into capital X minus b, and the error function is denoted by f, which is sum of square of error for each of the terms. So ax minus b will basically have 5 terms or n terms. Here n is equals 5. So f is basically the sum of all these error terms. And next we calculate gradient of f using f dot gradient with so this will calculate with respect to x. So x0, x1, and x2 variables. And if I print all this, this is how my error term looks like. So my error is a 5 by 1 vector. My function f is basically sum of square of all the 5 terms of the vector, and then I calculate gradient of f as basically gradient of the sum of squares of error. Next, we wish to find the optimal solution. For that, we have to minimize the error, which basically means setting the gradient of f to 0. So that is done by solving for gradient of f going to 0. So each of the terms of f, gradient of f go to 0 in the range for I in the range m. So like three terms. Solution with respect to variable x. So x, as we already seen, is x0, x1, x2, and the solution is returned in the form of dictionary. Once we do this solve, my answer looks something like this. And if I now calculate what the point x star is, it's basically x1, which is a vector uh, from the solution is based on the entries of solution S0. So this is what my x1 looks like, and my closest point to B is A into x1. This is what my closest point looks like. If I check how does this compare with, sorry, how does this compare with the, there, in this case they turn out to be pretty far apart. Okay, so this is how we can obtain a least square solution to the system Ax equal to B, which is not like perfectly solvable, but which gives us a point x star such that Ax star minus B, norm of Ax star minus B gets minimized. So that is basically the least square solution. Okay, any doubts with this example? We have been asked to find best fit quadratic y of x is equal to a plus bx plus cx square to a set of given points. The points I've already written down in the code cell itself. So we have a total of 11 points, as you can see. To get a sense of what we want to do, I will be plotting the points, only the points itself, using the point 2D function. So this is how the points look like. So any quadratic function would say roughly follow a pattern like this. To evaluate, uh, to find out this, to find out a solution to this problem, will it's basically a solution. It's basically similar to the earlier example, wherein we had a matrix Ax equal to B, and we wanted to find the best fit X. So in this case, what that means is basically A is a 3 by 11 matrix, wherein we take the value of I, wherein we take the value of 1x square for each row that creates the matrix A, and similarly we write a vector B which contains all the y values. So what do I mean is, I will I think I'll run this cell. I think that should make it clearer. I basically create a matrix A which has entries 1 comma x square for all the points. So the points go from x equal to minus 3 to x equal to plus 7. So we have total of 11 rows denoted by n equal to 11, and in each row we have 3 columns, 1 x and x square. To this 3 by 11 matrix, we will be say multiplying it with A, B and C. So that should basically create, uh, that should basically approximate this function y is equal to A plus bx plus c x square, and the we have to choose A, B, C such that our output y turns out to be closest to the y coordinates that we have for this particular example. So minus 60, minus 90, minus 40, and so on. Okay, as is a if like a unique or best solution does exist, we expect this vector B to belong to column space of A. If that is the case, to check that, like a good idea is to check that. So if we basically this returns false, which means that this particular vector B does not belong to the column space that we have here. To solve this problem, to get like the values of A, B, C fitting this particular equation, I will be defining x as a set of random variables of length m or 3 in this case, and from that I will be defining capital X as the vector of those variables. So capital X is x0, x1, x2. So now our problem becomes this matrix into x0, x1, x2 should be equal to this vector or get as close to this vector as possible. To do so, we'll be using like the least square approach itself, wherein we'll be defining error as x minus b into capital X minus b and function f as the sum of error for each individual term, sum of the square of error of each individual term. So my error should have 11 terms, whereas my f should have like square of 11 terms together. So this is how it looks like. Next, we define gradient of this error function grad f as f dot gradient. So this will automatically calculate gradient of f with respect to the series of random variables x, which is nothing but x0, x1, x2. So my gradient of f will have three terms as is seen here. Same process, minimizing the square of errors is nothing but setting the gradient of f to 0, gradient of error to 0, which is setting gradient of which is setting each term of the gradient of error to 0 and solving for x, which is the set of random variables x0, x1, and x2. We return the solution in form of dictionary, and this is how the solution ends up looking like. So from this I get the point x star as basically x1, vector x1, which is s0 of d or s0 of x0, x1, and x2 respectively, up to 4 digits. Sorry, 4 significant digits. So this is how it ends up looking like. And the point which is closest to b is basically into x1. This is how the point closest to b looks like. And to verify if this is like say a possible solution, I will be defining a function h of x, which is basically x1 of 0 plus x1 of 1 into x plus x1 of 2 into x square. So which is nothing but a plus bx plus cx square as defined in the problem statement. So this is how my h looks like. And finally, I'll be plotting all the points again using point to d function as well as the plotting the function f h of x for the range of points, which is -3 to +7. To show the plot ends up looking like this. So this turns out to be my best fit line for best fit quadratic function for the set of 11 points x comma y which have been given to us. Okay, so hope this example is also clear. So we basically so far we had figured out a way to write the quadratic function and taking the error. This time we are basically doing the same thing but from a matrix approach. Any doubts with this? If you have, you may ask them now. Okay, I think that is clear. So the next example that we have, example 12. Find polynomial of degree at most 3 that is closest to f of x equal to sine of x under the given inner product f comma g is equal to integral from 0 to 2 pi of the product of f of x and g of x. Okay, so what does this mean? So closest would basically mean that if we can say define any particular polynomial of degree 3, say a plus bx plus cx, cx square plus dx cube, and then take check how the inner product of f g f comma g varies with, sorry, is different from f comma f. So that inner product should the difference in inner product should be minimized. So that could be a way to that could be the way to define closeness. So inner product of f with respect to itself is the is basically by definition of sorry, f f is closest to itself, but we have been restricted to find another function g in the as a cubic polynomial of x. Okay, so let us see how to do that. So we first begin by defining the inner product in between f and g using the function inner product in as the integral of f of x into g of x with x varying from 0 to 2 pi. Next, we define norm of f, and we define both the norm of f and projection of f and g as square root of inner product of f with respect to itself, and projection as like the definitions that we have seen earlier. Inner product of g by inner product cg into g. Okay, the first function that we have is f of x equal to sin x. To define that, we like same process, define variable x, define f of x as sin of x. We will show the map of f as x going, show f as the map going from x to sin x. Next, I'm defining four variables a, b, c, and d, and then g of x is nothing but the g of x is nothing but a plus bx plus cx square plus dx cube. If I show g, it's the map going from x to the cubic function a plus bx plus cx square plus dx cube. Next, we define an error function. So error is, as I mentioned earlier, we want to look for closeness. So the metric that we have chosen is the difference between inner product of fg and inner product of f with respect to itself. Square of that should give us the error function. So error function looks like this. Next, we calculate gradient of this error function. So error function is defined with respect to four variables a, b, c, d. So the error dot gradient should have four terms. So the grad error has these four terms. Okay, and already one of those is going to zero. You can see that itself. So when we set when we are interested in finding a function, sorry, when we are interested in minimizing the error, we'll basically set the gradient error to zero. So we'll solve for the gradient of error going to zero, and it has four terms, and from that we'll be trying to obtain the four variables a, b, c, d respectively. So the function solution looks like this. So you can see that the solution has three parameters r1, r2, and r3 respectively for a cubic function. So the closest cubic function, capital G of x, would look something like r1 x cube plus r2 x square minus half of 8 pi square r1 plus 4 pi r2 minus 12 r1 plus 1 x plus r3. So it's like a three parameter function which by plugging r1, r2, r3 you can basically find the cubic function closest to f of x. If we want to say find simply a linear function which is closest to f of x, I again begin by defining variables a and b and g of x to be a plus bx. So the map g is basically x going to bx plus a. Same process error as the square of difference between inner product of fg with inner product of f itself. So this is how the error looks like. If I take the gradient, then one term directly goes to zero and we are only left with the second term. So for this term to go to zero, my b should be simply minus. A we can't say anything about it. So if I solve for this, my a is simply the parameter r4 and b is minus half. So which tells me that my closest function is of the form minus half x plus r4. So suppose I wanted to plot, so PLT is plot of f x going from 0 to 2 pi, and TLT I again have plot minus 0.5 x plus say 1 r4 equal to 1, x again going from 0 to 2 pi. I now show the plot. So we basically can vary the intercept, and each of these by the defined error function above, each of these will end up giving us the closest function. So the closest function is simply become like a set of parametric functions, but even if like it's a linear function. Okay, so any doubts with this example? Okay, if not, we'll move to the next example. Example number 13. Consider V is equal to R6. Let W be a subspace spanned by vectors V1, V2, V3, and V4. So we have been given four 6-dimensional vectors, and from this we have been asked to find the subspace W, which is basically linear span of these four vectors. And then we have been also told to find orthonormal basis for W as well as the orthogonal space to W perpendicular, right? And we have been told to use the standard inner product. So basically dot products between two vectors. Okay, we begin by defining vectors v1, v2, v3, v4 on the field QQ as specified in the example. And we also define capital V as QQ raised to 6. Next, we define a set L made of v1, v2, v3, v4. And then W, the subspace W is basically V dot span of L itself. So if I show W I get as a row space with like four independent rows. So like it has dimension 4 and with 6 by 1 vectors. Next, the W perpendicular I can directly obtain by doing like taking the complement space of subspace W, which is W dot complement. So again, an inbuilt function in Sage. This gives me W perpendicular. And if I want any basis, orthonormal basis, I'll just simply do W dot basis. And this will give me an this will give me an orthogonal basis. And similarly, W perpendicular basis I can do by doing this, right? And then I'm just checking if the inner product of B into C for a W for the basis of W and W perpendicular. What does it look like? So I should have 8 terms and all of them should go to 0. This is what I'm saying. Okay, so okay, made a mistake here. I actually thought that this was only an orthogonal basis, so solved it for orthogonal basis. But as we have seen in the earlier examples, we can do the same process. We basically we basically take the norm of uh, each of the orthogonal components. So if I write WB1, WB2, WB3, WB1, WB2, WB3, and WB4 equaling W basis. And if I do WB1 dot product, that of and do WB1 dot product, WB1 dot product, WB1. WB1 is WB1 by square root of the inner product or square root of the norm. So if I'll just repeat this step for all the four bases, I should be good to go. 3, 2, 3, 4, 4, 3, 2. So it should not affect WB1 and WB2, but and because I'm doing it anyways, I'm just writing out the whole thing. So this is how the ortho normal basis would look like, and same process I can just repeat for the perpendicular base to obtain orthonormal basis for that itself. So okay, so that should give me orthonormal basis for W and W complement respectively. Any doubts with this example? Okay, it seems it is clear. So the next example we have is regarding generation of a random 4 by 5 matrix A, and for that we want to simply check what the rank of A into A transpose looks like and if it is indeed equal to rank of A itself. So I write down M and N as 4 and 5 respectively, and A as a random matrix over the QQ field with N comma M. So if I show A, this is how A looks like, 4 by 5. Right? So 4 rows, 5 columns, sorry. And rank of A turns out to be 4. I do A transpose as A into A transpose. So A transpose is a 5 by 4 matrix. So A transpose is basically 4 by 4. And if I check its rank, A transpose is also 4. So I can just do this for other random matrices also. Right. So this is how it, like simple relation has been verified. I think that this is quite straightforward. The next example that we have asks us to find SVD, singular value decomposition, for a 3 by 3 matrix given as follows. So A is now a matrix on RDF with the entries given here, and to obtain the singular value decomposition we simply do A dot SVD, and From this we get U, S and V, where A is U into S into V transpose, or U into D into V transpose, depending on what notations you use. The matrices look like this. So U is a 3 by U, S and V are all 3 by 3 matrices. If I do U into U transpose and V into V transpose, those basically correspond to I eigen right eigenmatrix of A transpose A and A into A transpose respectively. So just to check that, I'm calculating A transpose A eigenmatrix of that. So, and if I do A transpose right eigenmatrix of that, so this is how you can see that uh, you can see like U to be this minus 0.35 and 0.71, 0.59, and V to be minus 0.81, 0.53, and zero point 0.6 minus 0.26. So basically, eigenmetrics of A transpose A or A transpose, respectively. Okay, straightforward example, this one also. Next, we have been asked to find least square solution for Ax equal to B using generalized inverse or pseudo inverse. So A is a 5 by 3 matrix, B is a 5 cross 1 vector. We have been asked to calculate generalized inverse. Uh, calculate, find the solution X for X equal to B using the generalized inverse. We define matrix A and B using RDF respectively. So like the entries have been filled out, and if I just show A and B, this is how they look like. So we have defined it. Next, we perform singular value decomposition of A. That should give us US and V matrices. If I run A.svd and print out the outputs, U is a 5 cross 5 matrix, S is a 5 cross 3 matrix, and V is a 3 cross 3 matrix. So A is basically USV transpose. Next, to calculate pseudo inverse, I need to calculate inverse of S. So S inverse is basically identity matrix by S. So we have a 3 cross 3 identity matrix, 3 diagonal terms here, and so just to check if that is the correct inverse, I am basically doing S inverse into S. So if I do S inverse into S, it gets me back the I3 identity matrix, and if I do S into S inverse, I get a diagonal matrix with first 3 entries and 1 and the next 2 going to 0. So this is how my S inverse looks like. And then the pseudo inverse is nothing but V into inverse of S into U transpose. So we have defined A as US V transpose, pseudo inverse of A as V S inverse U transpose. So this gets a pseudo inverse of A. To check, we will check the multiplication of pseudo inverse of A with respect multiplied with A. So pseudo inverse of A multiplied with A, you can see that the off diagonal terms are nearly 0. This gives us 1, 1, 1. So I3. So whereas A into pseudo inverse doesn't give us I3 or I5. How do we use this? We have seen that pseudo inverse of A into A is I3 and we have Ax equal to B. So if I pre-multiply with pseudo inverse of A on both LHS and RHS, I get A pseudo inverse A, X is A pseudo inverse B, which means my least square solution X looks like pseudo inverse A into B. So my least square solution, as I mentioned, is pseudo inverse A multiplied by the vector B. So if I show XLS, this is how it looks like: 0.285 minus 0.44 and 3.77. This is quite some, uh, and my closest point is basically A into XLS. XLS show. So my least square solution is quite some point far away from me, but this is how we can use the generalized inverse or pseudo inverse to obtain solution of closest solution of X. Okay, any doubts here with like the pseudo inverse concept, how we have calculated? Okay, cool. So I think this is clear. If you are interested in, maybe you have done this, maybe not, but if you are interested, you could pick up, say, a good book on linear algebra and check out what pseudo Moore-Penrose pseudo inverse basically is. That will give you an idea how we basically obtain this least square solution. Okay, final example for the day. We have been asked to solve a system of ODE x dash is equal to a into x, where a is a 4 by 4 matrix that looks like this, and x is initialized, or x of 0 is 1, 0, 2, 3. Okay, we'll be doing it two ways. Firstly, by using something called as like a system of differential equation solver, which is inbuilt, and then using the diagonalization approach. So we specify the matrix A Q in the field QQ with all the entries, and x0 as a vector with the relevant entries. This gives us matrix A and initial vector x of 0. With the inbuilt function, I am defining first the time variable t, x1, x2, x3, and x4 are functions x1 of t, x2 of 3, x3 of 3, and x4 of t respectively. So I'm defining four functions corresponding to the four values. So my basic equation becomes x dash is nothing but dx1 by dt, dx2 by dt, dx3 by dt, and dx4 by dt respectively. And that is basically this matrix A into x1, x2, x3, and x4 at time t. Now, the first differential equation is the differential equation of x1 with respect to t. I am just multiplying the first row with x1, x2, x3, x4. So that gives me this equation. Similarly, differential derivative of x2 with respect to t, x3 with respect to t, and x4 with respect to t are defined. So we have four differential equations: d1, d2, d3, d4. Now I solve them using the inbuilt function dsolve system. So the four equations are d1 to d4. For variable, for functions are x1 to x4 of t, and the initial condition contains the initial value of t, which is t equal to 0, and the initial value of x1, x2, x3, and the value of x1, x2, x3, x4 at t equal to 0. We are telling it that the independent variable is t. Once I do solve, I get like a bunch of equations, and what I'll now do is I'll just rearrange them properly in the form of a matrix. So my x1 of t, x2 of 3, x3 of t, and x4 of t is basically this 4 by 1 vector. Okay, straightforward using the dsolve system inbuilt function. But if you are interested in using the diagonalization approach, we first calculate the eigenmatrix A, eigenmatrix decomposition of A, which is basically A into P, which is basically A into P is P into D. So the diagonal matrix T and eigenvector matrix P are specified here, and just good practice to check AP equals PD. Next, we define the matrix dt to be basically the diagonal matrix multiplied with the term t, and we raise it to the exponent. So my matrix looks like exponential 3t, 2t, minus t, and minus t. And finally, my capital X is basically, if I rearrange this, A is basically P inverse, and uh, since I know Ax is equal to, sorry, dx by dt is equal to x, my x is basically p into this exponent matrix into p inverse multiplied by my initial condition. So if I just run this to calculate capital X and then show it in matrix form and just take the transpose, that will give me a column vector. So this is how my solution looks like. Okay, so both approaches lead to the same solution, whether it's diagonalization or the system solver, uh, and that basically solves this equation. Any doubts here, or any of the examples that we have seen earlier? Okay, if there are no doubts, then I think we can stop. If you have any other doubts related to whatever has been taught, you can ask them also.